My name is Oliwier Melon. I'm a DPhil student at the University of Oxford, supervised by Maurice, Fallon and Ioannis Havoutis. In collaboration with Mathieu Geisert and David Surovik, I present our work on reliable trajectories for dynamic quadrupeds using analytical costs and learned initializations. Motivated by dynamic animals capable of making informed, intelligent decisions, we can identify a number of objectives for motion generation in robotics. These include long horizon planning, adaptability to terrain, gait adjustments, and the leveraging of momentum. Modern applications require dynamic robots capable of efficient and quick traversal of complex terrain seen in industrial and disaster settings. We propose an approach that makes progress towards these challenging goals. I will start by introducing numerical trajectory optimization and the trajectory optimization library for walking robots, which acted as our starting point to this research. I will discuss our proposed approach, emphasizing the contributions of our work and the implementation which relies on analytical costs and learned initializations. Then, I will analyze the results obtained in simulation and on hardware. Finally, I will highlight the limitations of our methods and how we are addressing them. Trajectory optimization is a process of transcribing a continuous time problem into a discrete nonlinear program. Using a method like direct collocation, it converts the decision variables from vector functions to real numbers. It limits the dimensionality of the problem and changes differential equations into algebraic functions. The NLP typically describes the state using cubic Hermite splines made up of third-order polynomials defined by nodes and their derivatives. It can be solved using an interior point method solver like IPOpt, which solves a constrained, nonlinear optimization problem made up of an objective function f, inequality constraints g, and equality constraints h. Iteratively, it modifies the nodes and their derivatives to obtain a feasible, low-cost solution. This results in a set of splines that describe the motion of a system. In this work, we use TOWR, a trajectory optimization library for walking robots. It formulates an NLP to find the base linear and angular position. What distinguishes it from other libraries is the ability to simultaneously determine the durations of stance and swing phases, allowing for arbitrary gaits to be discovered. It determines the feet positions with respect to the terrain and the ground reaction forces. Notably, the software formulates a feasibility problem using only constraints and no costs. The problem is constrained by the desired final pose, the dynamical model of the robot, the kinematic limits represented as boxes around the feet, and the total duration of the trajectory for a given number of steps. In stance, when feet are stationary, the exerted force must lie within a friction pyramid, while in swing, no force can be applied. Once the NLP is constructed, it is optimized to satisfy the aforementioned constraints. The resulting splines can be discretized to produce base and feet trajectories. However, numerical feasibility does not guarantee viability. We augment a trajectory optimization library TOWR with analytical costs. We initialize the nonlinear program using a neural network trained on terrain. We realize this approach on hardware using an adapted whole-body controller designed for the animal. Thanks to the third-order polynomials of Hermite form, we are able to analytically compute integral costs and the corresponding Jacobians required by the solver. In the bottom video, we demonstrate the effect of minimizing the angular velocities of the base, the linear velocity in the z dimension of the base, and the derivatives of the components of the ground reaction forces. We constrain the height of the swing using a constraint and a differentiable Gaussian cost placed on the corresponding optimization variables. Our approach, shown in the bottom video, can find trajectories to avoid such a collision by penalizing stepping close to the edge of the pallet. The inclusion of costs results in trajectories that are easier for the controller to track accurately. The introduction of costs increased the optimization time by requiring a higher number of iterations to converge to a solution. Many trajectories reached the goal and showed good qualities, but due to the extreme nonlinearity of the problem, others became stuck in bad local minima. To overcome these problems, we resort to using a neural network to initialize the primal variables of the NLP. Next, I will focus on our learning method, which greatly reduces the computation time of the planning. To maintain the same number of optimization variables, the total duration, number of steps, terrain, final base pose, and final feet positions are kept constant. The network models the relationship between initial conditions, base x position, y position, and yaw orientation, and solution trajectories consisting of all optimization variables. The training data was obtained using the heuristic initialization of the NLP, which produced a large set of offline trajectories. The cost associated with each sample trajectory, starting from a different grid location, was computed. Due to the extreme non-convexity of the problem, some poor quality outliers occurred. The high-cost trajectories were excluded and only the good outcomes were considered during the supervised learning process. This produced consistently valid trajectories. We named this approach Learned Init 1. To further improve the quality of the initializations, we used its low-cost initial guesses to retrain the network. We saw further performance benefits when the process was repeated for the second time to create Learned Init 3, our deployed neural network. With the heuristic initialization, many tasks diverge, producing high costs and forces. As shown in the plots, the learned initialization resulted in convergence to low-cost, feasible solutions within fewer iterations, which gives a greatly reduced online computation time. The various initializations were compared in simulation. In the lower figures, the success curve of the heuristic plateaus at a low value due to many divergent cases. The learned initializations help avoid this divergence and have high plateaus, even if phase durations are being optimized. The curves are shifted left, implying that very few iterations are needed to reach a given level of performance. These iterations are performed during the online refinement. To validate our approach on hardware, we fully implemented the whole system on the animal quadruped. We tested a number of dynamic trajectories on flat and complex terrain. The first set of tests involved trotting on flat ground. These 3.5-second long trajectories were created in less than a second. We asked the robot to climb a pallet. We then repeated the test, but without any refinement. The network provided the 5.5-second long trajectory almost instantaneously. To demonstrate the ability to plan the trajectories on non-horizontal surfaces, we used the ramp in our setup. Lastly, we increased the difficulty trying to climb a double pallet. As indicated by the second video, using the learned initializations, we were able to generate a 5.5-second long dynamic trajectory in less than 2 seconds. Without it, the optimization would take 10 times longer. In summary, the contributions of this work are the generation of reliable trajectories using analytical costs, the speeding up of the optimization using learned initial guesses, and the validation of the proposed approach on the animal quadruped. However, there are some limitations we have to address. The framework plans the trajectories of a given horizon in open loop, which makes it susceptible to disturbances. It requires prior knowledge of the terrain being traversed. Lastly, the learning was limited to a specific problem for which a single family of solutions was determined. Nevertheless, we are developing this framework further to address these issues. Our current approach performs replanning in a model predictive fashion. We are integrating the elevation map to eliminate the need for prior models of the terrain. We are building upon the learned initializations to address the multimodalities to make our learning more general and deployable for a wider variety of tasks. This work is titled Reliable Trajectories for Dynamic Quadrupeds, Using Analytical Costs and learned initializations.